Hi everyone, and welcome back to your next part of your the electronicsy type stuff. Okay, continuing on, we're going to be going over some terms and symbols and stuff like that for voltage, current and power. Just give you a brief run through on what I mean by power. Now then, oh yeah, I'll do a series of paradox circuits as well with the lamps, which I mentioned at the end of the last one. So first up, voltage is measured in volts. It's got the symbol when you measure it and you denote voltage as in volts. It's the letter V, so that's its unit. And when it's expressed in equations, things like P equals IR, P equals IV, expression for working out power ratings and things like that, how much power is consumed and whatnot, it's V again. Okay, so voltage is in volts and its unit is V. Symbol for volts is a little bit of a misty grey area nowadays. Used to be set standard, nowadays it isn't. There's lots of different variations. Now, whenever you showing a voltage in a circuit diagram, or you're looking at them, looking for voltage sources in circuit diagrams, they look something like these. So first up, we've got your traditional little node points. Okay, little circles with line coming off them. Line denoting, that's where your track begins, and the circle saying, this is where power is. Normally there's two of them. Why? Because all voltages have a positive and a negative, or a positive and a zero. Top one is always your reference to positive, bottom one is zero. If it was a negative voltage, then the top one would be zero and the bottom one would be a negative. So negatives go to the bottom, positives to the top, zero somewhere in the middle. Typically it's shown with an arrow in between the two terminals denoting polarity, and you also show it with a plus sign, and the bottom one, depending on what you're connecting to, whether it be a floating supply, so it will be negative, whether it be a fixed supply, so it will be 0 volts, and so on. So it will be plus V, minus V, or 0 V, or something like that, and the arrow denotes the polarity, or the direction of the potential, if you like. So that's that one. That's what in quite a lot of diagrams. You see that in a lot of textbooks and things like that. If you're going for circuit diagrams, the whole thing containing resistors, transistors, diodes, op amps, and blah 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 blah, whatnot. Okay, sometimes you'll see it like that if it's a very basic circuit. Other times you'll see it like this. You'll get either arrows or you'll get T's, and you'll get arrows pointing up, arrows pointing down, T's upwards, and inverted T's, which are actually upside down capital T's. The arrow denotes polarity, so arrow pointing up, like this one, means that it's a positive voltage. And these ones have got a lot of different terms. You can have V, VCC, or VDD, and there's other variations like VD, VA, and so on. So those abbreviations, so everything's in V for volts, obviously, plus V, and it's how it's connected in the actual circuit where you've got all the subtext. So VDD would be for transistor technology, things like BJTs. VDD will be for, did I say VDD? We'll do that again. VCC for positives for transistor technology. VDD for things like FETs, JFETs, MOSFETs, and so on. Why? Because your transistors have got a collector, so the collector is connected to positive, hence VCC. Your FETs will be your drain and what have you. reference connected to your positive. Other ways, instead of the arrow you can have the T, and all of these are positive voltages. On the other hand, there'll be a reference to your 0 or your negative, so your negative voltages will be T pointing downwards, or arrows pointing downwards. And again, that has its own definitions as well. Voltage, again, a V for everything, but your subtext will change. You could have a VEE, that'll be the BJTs for emitter voltage connection. VSS, which will be your source on your FETs. So that's where that's connected to, but it's actually the opposite way around on FET. So you connect your source to VDD and your actual drain to VSS. Yeah, like I said, it's a grey area, so you have to be very, very careful on. And it's always best if you're doing the circuit diagram, always put a plus, a minus, or a 0 in place of those. Now then, 0 is a little bit of an arse to deal with because it's completely been turned upside down on its head. People that don't actually know what we mean by 0 volts. Now you've got, I'll do an entire video on this basically. I'm talking about earth, chassis, ground, and 0 and minus. All these ones, minus the floating supplies can be your reference, so that can be denoted as 0. You have to be careful of that. Earth, a lot of people use earth as being a common reference point, but the circuit isn't actually connected to earth, which is a complete and utter laugh. And that all boils down to bloody simulation packages which say, oh, you must have an earth reference connected to the 0 volt line, blah blah blah, in order for your simulation to work. Well, that's complete utter bollocks. You don't need that. And yeah, I absolutely detest it when you start getting into trouble like that, because you've got people that programs that design software, but engineers use it and we know, oh, that's wrong, and we go back to the program, try and explain what 0 and earth is and all this sort of stuff, and it just confuses the hell out of them. So sometimes you can have the earth symbol. Next one, chassis 1, very similar to the earth. It's a reference point, it's 0, it's what you will reference to, so you've got plus 9 volts to the chassis, which will be a similar thing to your car. Car is a floating voltage. It is connected back to the battery, but generally the chassis of your car is connected eventually back to the negative of your battery. So you can, if in doubt, you can connect onto the chassis of your car. That's why sometimes you get your lights sort of like intermittently working, because I'll actually end up with ground loops in your car because we've got things connected back to the chassis, and yeah, all sorts of weird things start happening if you don't connect things up correctly. And the other one is your 0 winch, is your node reference again, and so on. So they're all your symbols. It's all a mixed bag, and it takes time to sort through them all. So that's just a little bit of a heads up. As we go through doing circuit diagrams, you'll get used to the terminology and everything else, and the symbology to it all. Next up, current. Current, what flows in your circuit, is expressed in terms of amps. So you've got 1 amp flowing in your circuit, for example, and the unit for an amp is A. It's the letter A, capitalised A, so it will be 1A is equal to 1 amp. Simples. In equations, we start using expressions like your P equals IV. It's the equation for working out power again. Well, current is denoted as the letter I. Some texts have it as lowercase I, some texts have it as uppercase I. I normally use it as the uppercase, so that's the default set standard. Again, things are starting to grey a little, and it's not great, but yeah, capitalised I. Measuring it in amps, and the symbol is the letter A. Symbology time again. For current sources, they're normally like stated like this. Actually, go back. Quick point. Voltage sources, don't ever use a B in a circle and denote it as plus. That's actually a bloody voltmeter. I've seen lots of people do that. Don't do it. Right, saying that, back to current. Current is denoted, the current source is this thing up here. It's two circles overlapping. And again, you would reference it with a plus, no arrow this time, because it's a current source, it's current that's flowing. Okay, so if you have a current source instead of a voltage source, that's what you use. Denoting currents flowing in a circuit, there's only one way to do it, and it's this way, and that's an arrow going in the direction that current flows down a track. So if that's your track, have an arrow on it, that's current flow, and next to that you'd say 9A, 9 amps, 1A, 1 amp, and so on. It's the only way you can do it. Doesn't matter what circuit it is, it doesn't matter what the hell you're doing, that's the only way. Last but not least, power. Right then, back again, just had the alarm go off, bloody pain in the arse. Right then, last one, terminologies crap I'm going to go over is power. I mentioned P equals IV. Power equals current multiplied by voltage. Power is a multiple of those two things, and power is the energy required for a system to operate. You've got power coming in terms of voltage and current, and you've got power going out. Power being consumed, I should say, from the circuit in order to get it to do different stuff. And it could output that as light, heat, whatever, radiation, what you know, sound even. So it's power in, power out. Power is energy. Yes, the stuff that we use in order to make our bodies work and everything. It's the same stuff. No different. Power is equal to energy, essentially. I'm not going to really go over that. If you want to look it up, fine, go ahead. Power, the stuff that goes into your circuit, okay, that's supply. Power drawn out is power consumed, and all components consume power, and they dissipate power. That's power dissipation, power consumption, so on, power required, all that sort of stuff. Power is a very big thing in electronics. Terminology, power is measured in watts. Okay, so that's how we express power. And in equations, it's the letter P for power, and its unit is W. Okay, so there we have it. Symbology, there's not much symbology for it, and it, that's one of the big buggers. You can't really, there's no symbols for power in circuit diagrams for express power. Normally it's just given as a value for a particular component, so something like 0.25 watt resistor is the maximum wattage that a resistor can dissipate. In other words, for a resistor it's heat. As you drop a voltage across a resistor, you pass a current through it, it does heat up to a degree, and that heat is described as power. And so that's power, and we're all covered with that sort of stuff. I'm not really going to go for any of that. From now on, we're going to go down to the bench and do series and parallel circuits with lamps, so you can actually see what I mean and what we mean by a series and parallel circuit. So here we go. Okay then, your first circuit, here it is. One battery, positive is the red wire going to one side of our bulb, negative will go to our opposite side of our little lamp. So this is our voltage source, and our current is going to flow down our cables when I connect the circuit. So at the moment it's open circuit, nothing is working, no current flows. As soon as I close the circuit, if it will go in the hole, so I can let go of the component for you. Okay, there it is. We closed the circuit. We've now got a current flowing through our bulb down to the opposite end of the battery. So we've got a circuit and the light is on, just showing you that we do have a current flow. Now then, this is the basic circuit. It's just connecting at one point to the opposite. And what we mean by series circuits is we join components in a line. So we've got, in this case, two lights connected together. So we've got one wire going to the positive through the bulb, and then the other wire connected to the other side of the bulb through the next bulb, and the wire coming off to here. So when we connect that up to our negative, two bulbs light up, and what we have, okay, is a series circuit. Current's flowing through this one, down the wire, through this one, back to the negative of our battery. And yes, the lights are a lot dimmer. Why? Because I've doubled up on the amount of bulbs I've got in series. This 9 volts was supplying just one lamp, so I had 9 volts across that single lamp before, and now I've got this 9 volts across 2 lamps, so effectively I've got only 4.5 volts now across each lamp. And because they're in series, I've also increased the resistance. The path that the current flows down is now, you know, we've got things in the way, you could think. Extra elements are in the way, so the current is being resisted to flowing, so the lamps are a lot dimmer. That's why they're a lot duller. That's what I mean by a series circuit. Things are joined one after the other. Okay, if this had a third lamp, then it'll be attached to the opposite end, and then off to the battery, fourth again, and it all goes in a line. Next circuit is the parallel circuit, and that's when you put things across components. And just disappear if I do that. And so that's what we got here. Sorry for the poor quality. Don't ask where the my camera stand's bloody gone. The tripod's disappeared off during the room move. Right, so what we got here, we've still got our 2 lamps in series here, and what we've done is we've done exactly the same thing here over here. So we've got our red going to up to here to both of these lamps. Now the current splits between down this row and this row, so we're now splitting the current, and we're rejoining back down here before it flows back to the battery. So it goes, so we've got path of current through that bulb, back to the battery, and we've got a path of current through this bulb and this bulb back to the battery. Now as you can see, there's absolutely no change if I disconnect this one between the brightness of these lamps. That's because we're working in parallel now, so it's the same voltage across in parallel, and the current drawn through each branch, it draws exactly what it needs to operate at as best as it can from the supply, which is back here. And that's basically what we mean by series and parallel. That's a parallel circuit where you've got components in parallel to each other. They're cascading, you could say, from the supply, and if we unplug that, that'll be components in series where you've got components in a row. Series, parallel. That's all that I'm going to touch on for that. And we're going to be doing more series and parallel circuits with other components. Not going to really go in depth into the filament lamp. Let's face it, these are a dying breed. When you come to be doing electronics yourself, if you're just starting out, by the time you've got around to building circuits and stuff like that, and you won't be using these, you'll be onto LEDs, semiconductor technology, and these will be out the window, because not only do these produce light, they produce a hell of a lot of heat, and that's wasted power. If we can turn more of that heat into light so they don't get hot, which is what LEDs do, be more power efficient. Your batteries last longer, you use less current, less voltages, and everybody's happy and more eco-friendly, and what you're not. So So instead of replacing that, you know, once a week, that'll last you months and months. Right. So moving on, next video we're going to be doing your first electronic component. Now I wouldn't class that as an electronic component anymore. We're going to be covering the resistors, so we'll be looking at the resistor itself in the first few videos, what a resistor is, what it does, how it's made, different types possibly, and then we'll be looking at it individually connected up in series and parallel, see how that makes a difference in the circuits. We'll be looking at Ohm's law further on, and we're doing potential dividers and current dividers and whatnot. And yeah, that will take up quite a chunk. And resistors, they're in every single circuit that you do, so that's why we're going to cover it next. See you next time.